at Penn College here in the BEE program. And for my senior project, I made a control system that evaporates water out of ceramic material. Over here you can see the stock ceramic, different sizes, different geometries. And the point of the system is to saturate, before putting the ceramic into the system, you saturate it with water. You take a mass weight of it, see how much the piece weighs. You put it into the chamber for processing, and then the ultimate product is going to have a change in weight based on the water that was evaporated. The evaporation happens based on a heater element inside, and gas flow that comes from a process variable. It was going to be argon. Unfortunately, I have compressed air right now. And basically the system is automated through a ControlLogix 5000 PLC software by Alan Bradley. Pretty common, very powerful PLC software. And this was donated to us for the school, and I incorporated this in my project. The system here operates on principles of control theory, PID loops, closed loop systems, and there's actually two separate PID loops in this system. There's one for regulating the atmospheric pressure, and there's one for actually meeting a temperature set point based on a user input. In my system here, I'm using Wonderware, which is a HMI pretty commonly used in the industry. There's a whole bunch offered. The school has two as of right now. Am I correct? I think it's Edusoft is one of them, and Wonderware.
Very. As UME, you can't forget that.
Yeah, absolutely.
Sure you can.
In this system, there's also panel view. I just did not incorporate it. I used Wonderware, and I designed the HMI, the system, the wiring, the whole design myself. And on this table here, there's schematics and basically process flow to see how the system actually works. On the HMI aspect side of it, we have a main screen here. The system runs in two modes, automatic and manual. If the system is in manual mode, we can assume control of each of these components. After safety interlocks are met, as you just saw there. So basically, once we achieve those set points, we load the ceramic piece onto the shelving, and then we can close this door. And after doing so, we insulate the interior of this device to properly insulate it through, thermal isolation. This would just agree with me, I'm sorry. This is a good time to ask about the weather. Sorry.
We're perfect when we all leave the room.
I say one camera.
Yeah, okay, perfect. So now that we're closed up, there we go. You'll see here that there's a limit switch for one of the safety variables. Before this process can even start, before you can apply power to any I/O, the safety requirements must be met, as with a lot of systems nowadays, because there's high voltage, there's heat, and other variables in this process. So we can close this chamber and we apply locks. This is atmospherically sealed with a Vidon O-ring to prevent air leaks. The thermocouples and the electrical feed-throughs are isolated with Teflon, so there's no atmospheric leaks and electrical isolation for safety. And once this is sealed, the safety requirements as far as the door limit switch are applied, and then the user has to manually engage the system with a green push button, and you have a indicator light saying that the system is in ready mode. The user can then select the operational mode, manual for testing, making sure I/O is working, and then at that point you have control of each of the systems. So I can actually open and close valves, I can start my pump manually, I can open my gas flow and adjust the process variables to make sure that my throttle valves in this situation are operating correctly. Once the user is ready to go with a recipe, we can bring up a recipe manager, and from this screen the user can put in different parameters. In this system I have 4 different segments. Each segment can go to its own temperature set point, a gas flow coefficient, as well as a segment time. So each segment you can specify if it's going to be a ramp to temperature or soak at a temperature. The way the logic works is if it sees a ramp segment active, it will ramp to the set point. Once that set point is made, it's going to progress to the next segment. If it's in a soak segment, it's going to check to make sure that the soak temperature is made, and then it will engage a timer. The timer will then proceed for whatever the user specifies in terms of minutes. After that process is complete, it will progress through 1, 2, 3, 4 segments, and then go to a final purge cycle that will basically bring this system to a user-friendly level because it's still hot. This system can operate to 250 degrees on a 2,000 watt heating element, and without further ado, I guess we can pick some values and start this. So for the sake of demonstration right here, we'll go to a set point of, say, 50 degrees C in segment 1. We'll open up the gas valve for 10% of 40 psi. Segment 2 will soak at 50% for 2 minutes. Segment 3, we're going to ramp up to 100 degrees. And then finally, we'll soak for 100 degrees for 5 minutes. We'll do 2 for the sake of time. And then the user can also pick how long the cooling segment will be in this situation. So we'll make this, I guess, 3 minutes for the sake of demonstration. And again, it's very adaptable for the user. So, you know, in these kind of systems, especially recipes, there might be processes that require different times. So this is kind of designed for a specific user interface. And basically, once this is done, the PLC has those values loaded in, and the system is then changed to automatic mode. And then we start this profile. You'll hear everything adjust to its set points, and after 10 seconds, the profile will start. That's basically done as a, oops, I made a mistake. You can go back in those 10 seconds and fix it. And now segment 1 begins. The red light over here indicates that the heaters are actually active. There's power flowing through these 2 conduits. The heater conduits are isolated through Teflon to prevent power to the actual chamber. The shiny silver side is actually active power. So I made sure to include a safety label saying "Do not touch." Because you know sometimes that kind of stuff is not really evident.
How's that worked out?
So far, pretty good. Also on the HMI side, we also have, when that is actually engaged, you will see a display message saying that the heaters are active. So the user will then be able to understand that when they approach, okay, I can't touch the conduits. I know what segment I'm in by saying the current segment value. And you can monitor your process variables here. So for example, while this process continues, you will see that the actual segment set point will be displayed, so you know what you're trying to go to, and your current level is actually demonstrated here. Now say that you want to know exactly how the system's behaving. I incorporated process flowcharts for historical trending. So over here, we can actually real-time data see how the system behaves at any given moment. There's a legend below here. It's a little small. I'm sorry that we're a little spread out today, but basically, if at any given moment an operator wants to come on and see, okay, what's the heater output at this current second, it will show you the actual analog value as well as graph that value right there. The whirring sound that you guys hear in the variation is actually the throttle valve trying to adjust and keep that at a partial pressure of whatever the segment is. In this case, my process segment requires a pressure of 700 torr. Atmosphere is 760. Right now, the throttle valve is adjusting itself based on a 4 to 20 linear signal to compensate for the flow and the input gas as well. So it meets a constant of 700. That requires some PID tuning, which can be a pain. I still had a little bit of a problem with the heater element. There's a little bit of overshoot, but it's something that I'm still kind of, it's a work in progress in terms of the heater PID. And basically, now that we met that set point for segment 1, we're now soaking in segment 2, and the reader can see that there's a display for the current segment. So we can actually see this progress through its cycle as it goes on. In addition to this, we can take a look at the logic here. Using the RS Logix 5000 software, I incorporated this whole program in a series of subroutines. One for manual mode operation, one for automatic, and then there was some safety ones I also included for just in the event of an overpressure situation. We have some I/O in the back, a differential pressure switch. If the pressure in that chamber becomes over positive atmosphere, it's going to trigger a purge exhaust valve that's going to automatically vent out to prevent a overpressure condition and, God forbid, blow anything up. We also have in this system the DIN rail panel, which is getting its commands from the PLC software. There's a schematic of this DIN rail system over here with each reference node. Basically, it's a series of contactors and DIN rail terminal blocks that just route the appropriate control signals to the proper I/O. And we also have some additional safety on here. For example, the E-stop, if that is depressed during the cycle, it will cut out and go to a final purge cycle. There's also an emergency stop on the HMI that will actually, using a master control relay in the software, cut all outputs of the system. And inform the user that there's been a condition met for that. I also have two sensing thermocouples, one for the process and one for safety. In the event that one thermocouple breaks from deterioration or there's a hardware problem, you don't want to just open that up if it's, you know, a very volatile temperature. So we also have that backup sensing. Another safety routine I also implemented in here is that if the user accidentally loses communication between the HMI and the PLC, typically that's done through a watchdog. I did not have that in the system, but I did have a pulse timer that was sending out a second pulse every 3 seconds. And if that was, if the script was seen by the HMI to the PLC, it would continue the condition of communication is true. A lot of times these systems can be very complex and can use very volatile gases. There was a couple companies that I worked for that used large-scale systems like this, but with gases like hydrogen. And those kind of situations, you know, you can't take guesses. You can't really be very nonchalant about it. That's, you know, that could be property damage or even loss of life. So that kind of stuff is extremely important in PLC interlocks and safety, and making sure that you at all times know what's actually going on in this kind of process. Currently, right now, we're in segment 3. We look at the historical trending again. We can see that this is actually the output of the throttle valve PID. It's not exactly adjusting 100% to the gain. There's a little bit of deviation. This red line over here represents the overshoot of the heaters. The set point is the blue, so you can see there's a little bit of a PID adjust that needs to be done. But again, this is a great tool for, especially in industry, to see, okay, if you set this system and say it's running for a couple hours on end, well, you might not be there when it fails. Having a historical trender, you can go back and find out, okay, when did this segment fail? And why did it fail? You can look at your process variables and find out, well, when I was away, you know, during the night shift at 2 o'clock in the morning in segment X, I found out that my heaters stopped getting a receive signal. So then you have a means of narrowing your troubleshooting process to one specific segment. It's a great kind of feedback for the user to find out exactly where they can adjust themselves and find out where they can at least start to tackle the problem. Additionally to this, there was the software that I used for communicating between the HMI and the PLC was an OPC client known as Kepware. There's tons of them out there, but this is the one that was on the system, so I just decided to use that one. It's a very good system. You know, everything was a really good learning experience, and this project involves a lot of process segments from and rigors from the major. We learned about control theory. We learned about, you know, obviously HMI and PLC automation, sensing and control, closed loop systems, and all of that is a very good mixture in this system. We have a little bit of everything in here, and from the ground up, you know, even from the design aspect all the way to the final implementation, every piece is very crucial off of good engineering from the start. As you guys all know, I'm sure, if you don't have something as simple as a block diagram from the start, you might have someone coming to the system to troubleshoot, and you know they won't know what the system's supposed to do. Well, having process flowcharts will then show you, okay, the system should behave like this in this condition. Why isn't it? You hand those to an engineer, and he'll be able to interpret that flowchart and translate it into HMI or PLC logic. We're in segment 4 right now, and this segment we are supposed to be soaking for 2 minutes, so we're just about done with the last segment, and we're going to go to a purge event. While we're waiting for that, is there any questions I can answer?
How did you come up with the application? Do you have some work for some company that did something like this?
Yeah, I used to work for Kimmer. They make handguns and rifles and shotguns. They're famous for their 1911s, and they use this in the metal injection and plastic field. Basically, in a process called debinding and sintering, these instead of using ceramic, they use a compressed mold of metal. For example, hammers for guns or safeties, barrel clips, all that stuff basically is used by a molding press, and in that molding process, after it comes out of that molding press, there's still a binding agent in there, a wax that basically holds the powdered metal together. Well, to get that wax out of there, you have to put it in one of these furnaces to debind that part. After that happens, you have to sinter, basically thermally anneal those molecules together so it becomes a hardened final product. And in those systems, they use gases like argon and nitrogen, hydrogen. They might use high vac systems depending on the application. Sometimes if you have a very rigorous metal like titanium, you might need to have a stronger pump in the high vac range. So a typical pump like this one is called a roughing pump. And this one can only pull about 30 inches HG. That's about 100 torr. So the maximum vacuum I can get is about 100 torr below atmosphere, about 660. Typically, when you have a process in the metal injection field, for example, you look at millitorr. That's 10 to the negative 3 torr. So, this is a very scaled model of that, but the theory behind it is very close to this application. Obviously, the amount of I/O may differ, the sensitivity of the process equipment may differ, but at the end of the day, it's all based on the fundamentals of process control and good engineering, habits from the start. This is taking a little longer than expected.
So this is your senior project. You have, going into some field, you know?
I love automation. I really do. I have a great appreciation for it because the possibilities are honestly endless, and it's just everywhere now. The mentality is that why would you have a human do something when a machine can do it with less error, twice as fast, and it's repeatable. And it's a trade-off. People have to get replaced by machines, but at the same time, and there's our process segment ending, and that's your final purge sequence. So we open up a purge exhaust valve on the back, and now we're blasting 100% of that argon into there and cycling through the cooler. And this is going to take place for 3 minutes based on our recipe. This light indicates that it's purging hot air, so someone in the back can understand that I shouldn't be back there because I might get steam or something, hot air in contact with myself. Additionally, it also lets the user know, hey, I'm done, or there was a problem with an overpressure condition. So every time that purge exhaust valve opens up, this is going to light up, indicating that the process is complete and that the chamber is no longer active in its process. And basically, once this happens, the user will get an on-screen message saying process complete, and the user can then reset the PLC through a soft reset on the computer, and they can start the next process. If there's any testing I/O, I didn't get a chance to work with it. On this project, I have had a little bit of experience with the RS emulator. Basically, if you're ever working for systems that you cannot afford to test physically on, for example, like a nuclear reactor, you don't want to start testing, live runtimes on that kind of stuff. So you use the emulator software to basically virtually simulate your whole process. And that's something I kind of want to get a shot at doing, especially if I'm going to expand any components or add stuff to this. But for now, there's still a little bit work to be done with the PID tuning. But this was basically done over the course of 6 months since December.
You have a job yet?
Not yet. No.
Poor people.
I'm still one more semester to go. December I'm graduating, and it's really up in the air if I'm going to go for a master's or. Yeah.
Where do you live?
I'm from the New York City area, New Jersey. Yeah.
You do everything in ladder logic, no function block?
Actually, the only function blocks, I guess, well, they're not really. You could call them blocks, like the loop statements, the timers, all that stuff. But I did want to check out the new, because this platform does support function blocks, and I do not have too much experience with that software programming.
There's a ramp, so.
Oh, is there?
Yeah.
I would have been.
What are you doing in the PID diagram?
It's all about the PIDE.
Yeah.
He thought about using it and ran out of time, so.
Yeah, well, the PID, in actuality, the PIDE is actually easier to tune
Is it really?
than a ladder PID. Yeah, I don't know why, but it is.
I was gonna.
It also offers auto tuning, but the auto tuning really sucks. Rockwell screwed that one up. Say that again.
I was honestly, I was told about the PIDE function block by Mr. Moser. He was a very big help on this whole project, and basically, I was going to use that because it supports cascading PID blocks. So I was going to use that, but I didn't have the time yet to go through that. It's something I definitely want to try doing. In this kind of field, you always have to be on top of technology, and you can't just have a solution and have it work for 50 years. Eventually, someone's going to find it cheaper and better way to do it. So, this kind of software for me, there's a great appreciation I have for it, and there was definitely a lot of good things that came from this whole event.
How did you choose this project? Is this a corporate sponsor? Or?
Oh no, I mean everything was self-supplied except for some minor electrical connections and wiring, but everything else the valving, the chamber itself, the aluminum plate, most of the IO on the DIN rail panel was my own expenditure. Some stuff
to make the chamber.
it was just self-fabricated. Like we basically, I have a friend that's a welder, and he basically just gave me the dimensions based on.
Actually, looks like it's pressure coated. Is it done to code count?
Well, I mean, in terms of the thickness of the walls, yes. It's pressure vessels need to have an NF, the FPA, yeah. They have.
Actually, they call it the ASME code. But.
Yeah. They also have a OSHA specification for pressure vessels. That's the one thing I don't have on here is what's called a relief port. They typically have that mounted on the top of the door, and it's a spring-mounted mechanism that expands out if there's an overpressure condition. And it has to be, I think, if I'm not mistaken, it has to be, I think, 27% of the actual volume of the chamber. So at any given moment, if it does crack, enough of that's going to go out to vent whatever hazardous chemicals in there.
It's either going to be a pressure release valve or a rupture disc.
I'm sorry?
It either has to be a pressure release valve or a rupture disc.
Yeah, and that actually over here I had a quartz view plate, but it unfortunately broke. I was thinking I might always convert this, and now that the cooling's done, you can kind of hear better. I was thinking I might modify that, but it's still not to the actual specifications of the coating. So, but you know, it's always something I can add to. You know, for a first.
So how would you build over pressure? You're pulling a vacuum now, right?
No, right now, no. There's
No, when the
vacuum.
pump is running.
When the pump was running, yes, there
You're
was.
pulling a vacuum, so how would you overpressurize?
If the flow rate of the gas valve would be greater than the suction capacity of the pump.
Okay. Or if you start to generate steam off your wet ceramics.
Well, actually, I have two lines coming from that. Yeah, one is actually for the steam, and then one of them is actually for the air. This line goes to a steam. It goes to a plastic hose. The valve for you. Basically, you can see the condensation on this pipe. The steam will rise out through that and drain, while the gas is going to come out through this brass filter. So in the event where there's actually water accumulated on the heater element, I don't want anything shorting out. It was just basically one of those things where the gas has to be separated from the water. And typically they have traps like that for the wax systems, as mentioned earlier. In that debinding process for MIM, they have what's called a trap on the vacuum side of the chamber. And basically as it's pumping through, there's a portion of the vacuum line that can be isolated strictly for the debind process, which has to go through this trap. And it will, through a micron filter, suck the vacuum contents out, and it will trap that in a cold core trap, which is usually cooled through water or